Hey guys, I hope you're doing great. This is the second video of our ACD course on competitive programming, and in this video we are going to discuss exponentiation and modulo maths. So we'll be discussing binary exponentiation, or it's also called the fast way of doing exponentiation, and we'll also be discussing modulo maths, in which we'll be discussing the basic operation, that is a mod b, and the modulo inverse as well. So let's begin. And firstly, let's try to understand what exponentiation is. So let's say we want to calculate what is a multiplied by a multiplied by a multiplied by a, maybe like x times, right? So a way to write it would be a to power x, and this is basically the exponentiation. So this is the exponent. So this is the value we want to calculate. So how we can calculate it? We can calculate it in a very easy manner. So we can say that, okay, we'll start with a and we'll start multiplying it again and again, and we'll keep multiplying it x times. And the code also would be pretty simple for this. So let's try to just code it up. So let's say I have two numbers, that is a and x, right? Let's take it from the user, and then we can say from I is equal to 1, I is less than or equal to x, I plus plus. Basically we need to run a loop x times, right? And let's say my res would be stored over here. So initially my res is 1. In each loop I want to multiply a, right? So res multiplied by a, and at the end I can just print the value. This sounds good, right? I can remove this hello statement from here. Let's try to run this. Okay, I have to provide the input as well, which I haven't. So let's say we want to do 2 to the power 3, that should be 8. Yep, it returns a 8. Let's say we want to do 2 to the power 10, that is 1024. That is 12024, or maybe like 3 to the power 3, that should be 27. So yeah, that's working fine. But now the issue is, now let's say if your x was somewhere up till maybe like 1000, then it's fine. But what if your x was an insanely large number? In that case, you have to do that many times of like you have to run your loop that many times. It is possible that you'll get a TLE, or time limit exceeded, because the complexity of your code is actually order of x here. And let's say we want to reduce this. How can we do this? So over here, we're gonna understand a simple fact that let's say we want to calculate a to power x, right? Now two cases could arise. Now x could either be even or could be odd. The special case is that x could actually be 0 itself, right? If x is 0, then a to power 0 would obviously be 1, right? So if x is 0, then it's 1. If x is odd, right? So that is something we'll discuss later. But if x is even, then what would happen is you can say that, okay, if x is even, then we can divide by 2 and multiply it by 2, right? Another way of writing it would be a to the power x by 2 into a to the power x by 2, right? So basically, in order to calculate a to power x, we can say it's a to power x by 2 into a to power x by 2. Now, if we compute just one of these values, we can store it in a variable. So let's say we calculate a to power x by 2, and then we can say, okay, the answer is res into res. I hope that makes sense. And now what would happen is, so this is the case which we discussed right now, that is if x is even. So these are the values of x. If x is even, then that case would follow. So the values would become a to power x by 2 into a to power x by 2. The problem is if x is odd, then what would happen? Since if x is odd, then we can do another thing over here. So we can say, since your x is odd, then maybe let's subtract 1 from x, because as soon as you subtract 1 from x, then x would become even. So you can say it's a to power x into a. Okay, a to power x minus 1 into a. The way I'm doing this is, so this is a to power x, right? So you can say it's a to power x minus 1 plus 1, right? And this would translate to a into a to power x minus 1. Now since you have this, your x minus 1 over here, this x minus 1 is technically an even number. So now you can perform the same operation, right, that we did for evens. So you can say a to power x is equal to a into a to power x minus 1, and this is further equal to a into a to power x minus 1 by 2 into a to power x minus 1 by 2. I hope that also makes sense. And let's write it over here. So this would become a to power x by 2, x minus 1 by 2 into a to power x minus 1 by 2 into a. So yeah, these are the three cases that can arise, because a number can either be even or odd, and the terminating condition over here would be that your x has a value 0. So with that, can we write a basic function that is supposed to calculate the mods? Let's try that out. So let's erase it from here, and let's write a function called power, or let's call it power. So you want to calculate a to power x, and what I'll check is that if your x is 0, then just return me, if your x is a 0, then return me a 1. If your x is odd, in that case you have to return, let's not directly return it, but let's calculate the value for power of a comma x by 2, or you can say x minus 1. But once you have calculated res, you can just say it's return res into a, right? Else, the else case would only apply when your x is even. In that case, you can do the same thing, like you can calculate the value. Obviously you won't be doing a -1 over here, else you'll be getting a wrong answer. But after that, you can just return res into res. Yeah, surely let's print res now. Now, if you have coded the things properly, it should work. It should give you the same answer still. Let's see. Yeah, 3 to the power 3 is 27. Maybe like 4 to the power 2, that is 16. Let's calculate that. Or maybe 9 to the power 2, that is 21. Oh, sorry, 81. Yep, everything's working fine. So this is the right approach. Now let's look at the complexity. Look, by what complexity have we reduced it? So let's look at the approach again. So at every level, we're reducing the power by 2, right? At least by 2, I'll say, because at some places we are doing x minus 1 by 2, and at other places we are doing x by 2. So we are at least reducing it by 2. In that case, every time your power is being halved. And if your power is being halved, you can say that the overall time complexity would be log of n. For example, let's say your power was 10. In one iteration, you'll make it 5. In the next, you'll make it 2. In the next, you'll make it 1. Right? Let's check a bigger number. Let's say your power was 1024. Right? In one iteration, you'll make it 512. In the second, you'll make 256. In the third, 128. In the fourth, 64. Third, 32. Fifth, 32. Then 16. Then 8. Then 4. Then 2. Then 1. So you clearly see that the way of reducing it is in a binary format, and that's why it's called binary exponentiation as well. So the overall time complexity for this is order of log n. And initially, with a brute force approach, wherein we were running a loop, we were getting a time complexity of order of n. So we definitely have improved it from order of n to order of log n. That's a big improvement. But is this the best way of doing it? Technically, this would work, and I don't think this requires a lot of optimizations. But there's one more thing that you can use over here. That is the iterative approach. It's a bit faster, I'll say, because technically, when you're using a recursive approach, wherein your function is calling a function, internally, the way the system calculates it is a bit tedious. It makes your program a bit slower. There's another approach for this that's called the iterative approach. Now, definitely I won't code it up, but I still have the snippets on my system, so I can show you that. And also we can then talk about snippets a bit. So I'll just type math snip over here. So as soon as I type math s, this math snippet comes along. If I click over here, then a lot of code is populated. So over here, it's showing me a method that is power. And yeah, this is the iterative way of doing it. Now, how did all of this happen? This is a separate video that I've already created on the channel. I'll put a link of this particular video in the description. Definitely try to check it out, and these things would definitely help. Now, the only difference between this function and the one we initially wrote is that this is the iterative approach. It is supposed to be just a bit faster, right? Now, some things over here might not make sense to like what's gibberish over here. So this is essentially a right shift operator, but don't worry, we are going to cover all of this, but just not yet, not in this video. But yeah, if you want help regarding the snippets, I'll really recommend you to go through that particular video. Cool guys, let's get back to the topic. So the first thing is done, that what's binary exponentiation, and it was really easy to understand, right? Now the second thing is, what is modulo, right? Or what is modulo maths? So at times what would happen is that you'll be given a problem in which the answer could be insanely large. So your answer could be like 10 to power 100. How are you going to save this answer into a system? So approach over here is that you can take a mod. Taking a mod basically means that whatever your number is, so let's say your answer is num, right? You'll divide it by another number. So let's call this mod. Whatever remainder you get on dividing num by mod, actually your answer over here. Let's take an example. let's say you have 15, you try to divide it by 6, right? So 16 twos are 12 and the remainder is 3. So 15 mod 6 would give you 3. Let's take another example. Let's take a smaller value and then a larger value for the mod. Let's say you take 6 mod 8, right? The answer is simply 6, because if you try to divide 6 by 8, you can't, right? So you'll simply return the remainder to be 6. All these are basic stuff, right? But now what we want to understand is how do we do it in the system or in the language. So in the previous video itself, we discussed that in order to take a mod, you simply have to use the percentage sign. So if a and x are two numbers and you want to take a mod x, so you'll simply do a mod x. It's as easy as that. So 9 mod 2 should give me a 1. And it does, right? Now what are some other operations that you can do in mod? Let's try to understand those. So a plus b mod m is essentially a mod m plus b mod m, obviously whole mode, right? What if you have two numbers a into b mod m? This can also be written as a mod m into b mod m mod m. What if we take a different case wherein there is a subtraction? So let's say you have a minus b mod m. Now the difference over here is that you'll have to do a mod m minus b mod m, obviously, right, plus m mod m. But wait, why are we doing a plus over here? This plus is explicitly done so that whenever you're taking a mod m and b mod m, your values could technically change. Let's take a small example. Now let's say your a was 7 and then your b could be maybe like 5, right? So if you do 7 minus 5 mod anything, like mod maybe like 6, right, then answer would be 2 mod 6. That should technically give you 2. But this thing can change, right? So what if you internally mod it? So you'll technically do 7 mod 6 minus 5 mod 6 mod 6, right? So it would give you 7 mod 6 would give you a 1, 5 mod 6 would give you a 5 mod 6, and now you are having a negative value minus 4 mod 6, which doesn't exist, right? So this is not the way to do it, and hence we add a mod over here so that whatever value you are gonna get, so essentially it would become 1 minus 5 plus 6 mod 6, right? So whatever value you'll get, you'll at least have a positive value that would be greater than that, so that your overall value over here would actually at least be positive. So this would become now 1 minus 5 is minus 4 plus 6 is 2. 2 mod 6 would again give me a 2. Is this value correct? Let's check from above. So yeah, over here also you are having a 2. So this conjecture is fine and the answer is valid. Now what about division? The division is a bit different thing over here. Let's take three random numbers. Let's say 4, 8 and 12. Let's say we have a 12, right? And then we have a 4 and then we have 8. So let's say if we do the division first, then what happens is you'll get a 3 mod 8, which is 3, right? However, if I now say that I'm gonna do the mod first, then what I'll be getting is 12 mod 8 would give me a 4, right? And 4 divided by 4 would give me a 1. But these two values are not same, right? So you can't just do a mod like this. Like whenever you are gonna divide, you can just directly divide it when you're gonna take a mod later. So what can we do over here? So there's a theorem that's called Fermat's little theorem. It states that if you have a number a, then its inverse exists, that is a inverse, if and only if the modulo you are taking, right? The modulo you are taking and the number you have should be co-prime. We can come to this part later, but let's try to understand the basics first. So what essentially I'm saying is that if you were supposed to do something like a divided by b modulo x, right? So instead of dividing a by b, you can say I'm gonna multiply a with the inverse of b. And how can we come up with the inverse of b? For that, we have the Fermat-Slater theorem, but the necessary condition over here is that B and M should be co-prime. Only then it would exist. And in the last video, we already talked what co-prime numbers are. So co-prime numbers are those which don't have a common divisor. And in most cases, whenever you are getting a problem in CP, your M would actually be a prime number itself. Like I can say in majority of cases, the M would be 10 to the power 9 plus 7. This is a very famous number. This is also a prime number. So this would automatically be guaranteed, except for a very, very few problems wherein your M and B might not be co-prime, and it could happen that you have to use a different approach altogether. But in majority of cases, this would hold. So we should be good to go. But how do we calculate B inverse? So B inverse is simply power of, so power is the function we just coded, right? So B inverse is just power of B comma M minus 2. Obviously we'll have to take a mod, and we'll take a mod with M. This is all Fermat-Slater theorem states, and it is extremely, extremely useful. We'll try to understand, and obviously you'll be using it a lot of times, right? Whenever you'll be calculating factorials, or you'll be calculating not just factorials, but rather when you will be calculating permutations and combinations, it becomes extremely useful. And in your entire CP journey, you are going to use it a lot many times. So it's good to remember this, but even if you don't, at least have the code snippets so that whenever you require, you can just use it. So that's what I'm going to do right now. Now let's say we want to calculate the mod inverse of a number B. How can we do that? So I'll define a very simple function over here that would give us the mod inverse. Also, one more thing, while calculating mod, it's really easy that if you mess up somewhere, then your answer could be wrong. There could be overflows. So in order to avoid that, we actually can do what we actually can do is we can define our int to be long. Define int as long. Obviously the CPP compiler actually wants the main function should have a return type of int and not long. So in order to satisfy that, we can just use int32 type. After this, whenever we'll be using int, we'll explicitly be telling our compiler or telling the program to use long. So this should work. This should work well. And let's say one of the numbers is B and the mod is P maybe. And let's say its value is 189 plus 7. Now how do we calculate it? So we simply have to say, based on the Fermat-Slater theorem that we just learned, we can say it's power of B to the power P minus 2. That should be good enough, right? But the point over here is that I generally don't code the things up in the contest, right? So if I want to code the things up in the contest, I'll be using writing the mod inverse function, then the power function. So in CP generally you'll rely heavily on snippets, and we can use the powerful snippet we just talked about earlier. So I'll just use mathsnip and it populates. We can get rid of NCR, and we are using a uint over here that's unsigned int, but we haven't declared it. So let's remove that also. Also over here we can simply return int, right? And one more thing is, since I already told you that one of the most used mod is actually 189 plus 7. So let's define it over here, right? Const int mod equal to 189 plus 7, so that I can reuse them whenever I want. I just need to make a call over here. Now this program should technically give me the result of any number or the mod inverse of any number. Let's test it. So let's say I take the value from a user. So let's call that value A. And now I want the mod inverse of A. So let's just get the mod inverse of A. Right? Let's see the value. And yeah, let's say the value of A is 9. Let's see the value. It's pretty random gibberish, right? Let's like a lot of ones followed by 2. But how do we know it's the correct answer? A simple fact is that since it's the mod inverse, so since it's the inverse of a number, then if we multiply the number by the same number, then we should get a 1. I hope that's pretty common sense. Like you're just multiplying the number by its inverse, so you should technically be getting a 1, but you will also have to do a mod. So let's do that. Let's test our answer now. If we get a 1, it's all well and good. If we don't, then our answer is wrong. See, we do get a 1. Let's just test that how different could actually be the mod and its number. So I'll just save the values just to test how different these two things can be. So this would save the value for the mod inverse. So I'm just gonna say that the mod inverse is, okay, typo, inverse is this, right? And now let's validate it. Validate. Over here we'll simply do res into whatever the number was, that's a, taking a mod again. Now let's see. So now technically the system should print two numbers. Firstly, we should get the mod inverse of that particular number, and then we should get a 1 if the calculation of the mod was correct. So let's say we have a number that is 924. Let's try to run this. Yep, so the mod inverse was, I guess it's 8 million or something, and the validate holds. So the validate print statement says that it holds. Let's try with a bigger number. Let's try that. Yep, so we again get a bigger number, a much bigger number, I guess, and the validity of it still holds. So that's pretty much it about modulo maths and exponentiation. This topic is a bit easier compared to the previous topics we learned, because they also had a ton of problems that can be formulated just based on those problems. However, binary exponentiation and modulo maths are something that you're always or almost going to use every time when you're going to do CP. But we can't formulate a lot of problems just based on these two topics. So although I'll definitely attach some of the problems that can be solved using just these topics, but still they won't be that much that were attached with the previous video. So what I recommend is try to understand it completely. If you have any doubts, just ask on the Discord server or comment down below. Also, one request, guys, I would like you to like or dislike this video. Like, I'm not even asking you to only like this video. You can even dislike the video if you think that the content isn't good or there are some scope of improvement, because in that way I tend to understand where I am lacking so that I can provide more valuable content to you guys. And it's highly appreciated that if you find that the content isn't good, then you can just comment down below that what things could be improved, or if you find that the comment is good enough or the content is good enough, then you can just appreciate me. So either way, the entire motive is that I understand where my content is going fine or what are the scopes of improvement. Cool, guys, thanks a lot for sticking till the end. Hope you have a good one. Bye bye.